All right, welcome everyone to the Global Water Future Core Modeling and Forecasting Team Topical Webinar Series. My name is Praveen Rokhaya. I'm the Science Coordinator of the Core Modeling and Forecasting Team. It is my pleasure to present you today a webinar on collaborative and reproducible modeling. Today we have Dr. Gerard Bells. Dr. Bells is the Executive Director of the Consortium of Universities for Advancement of Hydrological Sciences, also known as QUASI. QUASI is a non-profit research organization representing more than 130 US universities and international water science related organizations. QUASI develops and operates infrastructure and services to broaden the water science community and increase the multidisciplinary collaboration for the advancement of water science. Prior to his position with QUASI, Dr. Bells was with the US Geological Survey as a chief scientist for water. In this position, he was the senior executive responsible for over $100 million of US dollar of activities related to planning and development of national hydrological research and technology transfer in US. Without taking much time, I want to kick off this webinar by thanking Dr. Bells for accepting our invitation and to present in this webinar series. The webinar today would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Dr. Bells, the floor is yours.
Well, thank you. Thank you for inviting me. This is pleased to be here. So I want to talk about collaborative and reproducible hydrologic modeling. And I will start with a quote from Water Resources Research. It was published in 2016. I think it was the anniversary issue of WRR. And, you know, there's an article in there I've linked to here. And the title of the article was, "Most computational hydrology is not reproducible, so is it really science?" So that's a motivating factor here for what we're talking about and what we're doing. And, you know, I think we can relate to that, especially when workflows are not particularly well articulated or shared with the community. And just to give you a couple of examples, I'll talk about two examples of where reproducible modeling failed. But when we talk about reproducible, we're really talking about the 3 R's of science: repeatability, replicability, and reproducibility. And so they kind of proceed, you know, from the simplest: I do an experiment, I repeat it and get the same results. That's the easiest, the simplest. But replicable is when your team tries to repeat my experiment and gets the same results. And reproducible is when we have a different team and a different experimental setup or modeling setup, but we're able to get the same kinds of results. So one example that you may or may not be familiar with, but in 2007, there was a comment published in Nature Medicine, and essentially the comment was that the authors could not reproduce a Duke University cancer study, a pretty significant study. And this kind of morphed into what has been known as the Duke Cancer Study. So as a result of this comment, and then the National Academy's Institute of Medicine taking a look at what happened, the Institute of Medicine put forward these guidelines in 2012. So it kind of took them 5 years to get through this analysis, but they said that computation should be locked down and repeatable using scripting languages so that any original set of data, all steps of analysis can be repeated and documented, guaranteeing robust data provenance and reproducible data management. So this actually was published, an article was published here in HES about this scandal and how it relates to hydrologic modeling by Finan and Baker in 2016. And then another example, a more recent one, is the pandemic. And if you remember a year or so ago, there were all sorts of forecast models about, what the number of diseases and deaths might occur in the next month or 6 months or so on. And I was part of a team that wrote a letter to science and was published, and it essentially said, these models are black boxes. We don't know, how people are getting results. The results differ significantly. People should share their code and their assumptions and so on. And, if you look even now at the current forecasts for the next, month or so, there's a lot of difference, and there's probably 20 plus models that people are using to forecast COVID. So COVID illnesses and deaths. So, these are really kind of important examples affecting human health. And so it's not, reproducibility is not just some esoteric scientific exercise, but it's a case in which, decisions about life and death and health are made in other disciplines beyond hydrology. But it certainly applies to hydrology. And as we think about, big data analysis, when we think about complex hydrologic modeling, reproducibility is quite important. And then this other little article, which I thought was kind of interesting. The name of the article is The Growing Inaccessibility of Science, but this is not readily accessible because you got to pay $9 to get the article. So it's kind of ironic, really. So we're at a point now where progress towards fair data, so fair data are findable, accessible, interoperable, and repeatable. So progress has been slow, and most of what people have done is focused on technical solutions, right? Metadata, standards, ontologies, and so on. But there's a socialization aspect of reproducibility and sharing data. And perhaps that's partly because it's additional work, partly because of misperceptions. But nevertheless, the societal benefits from data sharing are really not being realized because of this lack of socialization. So, as we said, I'm with Kawasi. This is how you pronounce it. That our name is sometimes mispronounced, but we are a nonprofit, and our members are institutions as opposed to individuals. And so our role is to empower the community by providing infrastructure for reproducibility in water sciences, and to promote education in water sciences, and to strengthen interdisciplinary collaboration, because hydrology really is a collaborative, multidisciplinary science. So I want to talk about one of our services in particular, and that's the HydroShare application. So you can find that just by going to hydroshare.org, and there you are, and you can get started. But the workflow for HydroShare is essentially shown here and from the home page. And so users create data, they upload data to HydroShare, they describe their data with metadata. We use Dublin Core metadata. The data can be shared. So for example, if you and I are working on a data set, I can share my data with you only, and then when we get finished and we're happy with everything, we can publish those data with a DOI through HydroShare. So a fairly straightforward workflow, but it's to make data discoverable, to make collaboration around data and models easier, and so that's the general approach. So when you go to HydroShare, you can create an account. Here's just sort of my account profile. Has my name, my affiliation, what I do. You can also include your link to your ORCID ID or to Google Scholar or other kinds of services like that. And so creating a profile, probably most things can be done in HydroShare without creating a profile, but there are a few things that really require you to create a profile. And honestly, profiles help us understand our community as well, and to reach out as we need to, and so on. But it's a pretty low bar to create a profile. And then, you can go to, once you're in HydroShare, you have your resources, which is right here. You can click on that and it brings up all of the data that, you have contributed to HydroShare. So here, an example of showing some of my resources that I've contributed to HydroShare. And this little figure right here, the little unlocked padlock, I guess, shows that the data is publicly available and accessible. And then these resources are shared with selected people. So here's how you can here's how you can curate your data and make the data available to those with whom you want to share the data. And you can, of course, over here, filter your data, the things that I own, the things that you have shared with me, and so on, as you search the data. And then HydroShare also, this is jargon, I guess, but it contains kind of 3 levels of participation. And so a resource is really just a data set, right? And so here's an example of a resource in which, this is for another user. It shows the resource listed. It shows the map where the data were collected, and you can search by location or search by data type or search by data provider and so on. So, but a resource essentially is data in HydroShare, and it can be anything. It can be a CSV file, it can be a TIFF file, it can be a Jupyter notebook, it can be any kind of resource, and so that's why we kind of call it resource instead of data, because it's in some instances it's more than simply a data set. But also within HydroShare, users can create groups. And so here's we have about 60 groups, I think, now. Users can create them and can invite members to that group to participate in the group. And so within the group, then users can share information, can communicate, and so on a particular topic. So here we have, just 3 examples. One is the Quasi National Water Center from National Water Center Summer Institute from 2000. This is an old one from 2017. A University of Washington Computational Hydrology class or group, and then the UCGIS Summer School in 2017. So if we look at the groups, you will see a lot how people have used HydroShare to work with particular people on particular topics. It facilitates sharing and facilitates discovery. And then the 3rd level of hierarchy is a community. So a community is really a set of groups. And so in this particular case here, we have the critical zone observatories that were in the US for about 10 years. And so over here, you can see the different critical zone observatories, Boulder, Calhoun, so on. But then the community is made up of a group of groups. So CZO Boulder would be one group, CZO Calhoun would be another group, and so on. And so this, in this particular case, we control, or the users control, administrative access to the data and who can upload the data and so on. So again, just to facilitate collaboration in the hydrologic sciences, a pretty important aspect. So again, the workflow, for example, would be, Jeff and Amber and Dave develop a study, they collect data, They upload the data to HydroShare. They do some analysis of the data using code, MATLAB code in this case for visualization and so on. They upload the code to HydroShare. They write the paper. The paper comes back. Need to revise it. So you already have the code and the data in HydroShare. And so you do the reanalysis, upload it back to HydroShare after downloading it and responding to the reviews. And then you publish the paper publish the paper and link the data and the code in HydroShare to the DOI for the paper. The paper and the codes and data are all linked together with the DOI. So another key aspect of HydroShare is the apps that we have developed and the community has developed. So apps, pretty much anybody can contribute an app to HydroShare, and the apps allow users to work with data in HydroShare using the HydroShare API, store the data back to HydroShare, and then, as I said, publish it. And so one of the things that's pretty cool that we're starting to do is using Jupyter notebooks and Binder. And so Martin Clark at University of Saskatchewan had a class last fall, 93 students from 17 different countries. And so Kwasi built notebooks so that the users could run a model in the notebook, without having to install anything on their particular machine. And so this facilitates just educational activities, but also facilitates, again, sharing code so that, when I run the model, I know that I'm using the same approach that you are. And so these are really very nice tools. And we encourage you to reach out to us and see how we can help you do that. And so here's just some of the tools that work that we use to work with HydroShare data. So we have this HydroShare GIS tool. So if for example, you were to store a GIS coverage in HydroShare, then you can use this app to open the GIS coverage within HydroShare. Others are OpenDAP, SWOTShare, which is a tool for running the SWOT model, a Jupyter Hub, and an app for looking at the U.S. National Water Model forecast data. As we said, anyone can build and add these to HydroShare, although we do curate the apps as they are added to make sure that they work for the entire community and so on. But this is a nice feature, and users can also just run apps outside of HydroShare, but within HydroShare, you can just go into HydroShare, and if you have a resource, you can click like right here and open with a web app, or other resources would be, I think, like here this is a Jupyter notebook, and so one would open it with Jupyter Hub, and then here's the data for that, and then this is just an example of the Jupyter notebook. So a mixture of text and code to do an analysis of topography, I believe this one is, and then so it's saved, the results are saved back to HydroShare and published again with a DOI. This is another, so I'll show you a few examples of apps here. This is another one. So Kwasi has developed a subcenter tool for the National Water Model and for Parflow CONUS. And so this notebook just helps users to work through that workflow. So for example, if you don't want to run the national water model for the entire CONUS or power flow, you just want to run it for your experimental watershed, then you apply the subcenter and do what it is that you want to do. So, and then this is just, again, a notebook. So a mixture of text here, and then an example of, of the code, importing the Python libraries, and so on. Collecting the NLDAS data, the streamflow data, and then running the simulation. Another example, this is using the LandLab tool. It was so the model capacity was developed for one particular location, but this notebook can be shared to run LandLab for different locations, and here's the publication on that in environmental modeling and software. In addition to the apps in HydroShare, we host a compute and modeling gallery. The gallery has examples of notebooks and MATLAB live scripts, web applications are Shiny, and so on. And so these are available for the community just to download and use if they want, or as examples on which community can build. So this is a fairly new capacity within capability within HydroShare that we make available to the community. And so here's a couple of reproducible science examples in this app gallery. And so you see this is the Python gallery and reproducible science examples. And click on that and we'll bring up the science examples. And then there's also the R gallery down here. And then finally, I think the last one on the show is about the SWAT satellite mission that's to be launched, the SWAT satellite to be launched in 2022, most likely by NASA. SWAT is designed, it's a surface water and ocean topography mission, and using a variety of tools, SWAT can be used to estimate discharge in ungauged rivers globally. But the constraint, of course, is there's a size constraint here. And you see on the right, the rivers at which SWAT can estimate discharge, and the rivers that are 50 meters wide or wider is the guidance. And so SWAT it makes a pass, it will make a pass about every 2 weeks or so. And so the tan colors that you see here are the SWAT orbital paths. And so you can, and then the points, the pins are USGS stream gauges. And so, for example, this is a stream gauge which is not, or this river reach right here is not observable with SWAT. So everything is not covered, but there is a tool in HydroShare. You can search for it based on the author that I showed a couple of slides ago. But this is a tool to say, okay, if we look at this stream gauge and we have synthetic data, or we generate synthetic SWAT data, what we think SWAT data will look like based on the particular location of the stream gauge and so on, what's the comparison between the observed and actual? And so this is a nice tool for kind of getting an understanding of working with SWAT data. And then when the satellite is actually launched and we start getting data, then this can be transitioned to looking at real SWAT data instead of synthetic data. So these are just examples of some apps that are available in HydroShare for the community to use. And it's also, again, HydroShare is a place where users can add other apps and, of course, their own data. So finally, just some guidance for supporting reproducible computational research These are basically common sense kinds of things, but it's maybe useful to articulate them, to keep track of all your results and your workflow, to avoid manipulating data manually. I think that was one of the problems with the Duke cancer research scandal was, the data, some data were dropped or cleaned up or, scrubbed because of various things. I mean, that's the case in which, you're working with environmental data. The data aren't always clean because sensors don't always work right or come out of calibration. Archive all the versions of the program, version control, and use scripts that can be reproduced, store the results in standardized formats, note underlying seeds. So, I mean, for hydrologic modeling, that might be, if you're running a model, it might be the initial conditions. If you run an ensemble, and people often run several ensembles using different initial conditions, store the data behind plots, generate hierarchical analysis that, the data can be examined using increasing level of detail, connect your statements, your textual statements to your results. So that's pretty easy and to find and to track how you reach your conclusions, and then make things available publicly. So this presentation is stored in HydroShare, so you can just go to HydroShare and search on my name, and you probably find it, should find it, and you can download it if you have an interest in that. So thank you for staying with me here. And for participating. I hope this is useful at some level. So, thanks.
Thank you, Gerard. That was a fantastic talk. We'll be now moving towards Q&A session. So I'll just give a few minutes for everyone to put in comments, questions. Before that, I wanted to ask you, how do you think the research landscape should look like in next 5 to 10 years, and what we can do as an individual and through institution to foster collaborative and reproducible research?
Right. So, I mean, I think we're kind of learning that working, one of the things the hydrologists have done over the years that they have worked in sort of their research watershed, right? So they instrument their research watershed and they study it, but that information is not particularly transferable. And some of the things that hydrologists have done is develop empirical models that we fit to particular conditions, and then we fit them to a different condition. But those approaches aren't working with the more complex problems that we're facing, and with the rapid changing water resources environment, right? So conditions are perhaps changing faster, with climate change, than we're able to keep up with research. And so it's important, I think, to improve our computational representation of the water cycle. It's important to do multidisciplinary collaborative work. I mean, again, in the past, we built levees to protect people from flooding on along rivers, but we didn't particularly pay much attention to the impacts of those levees on the floodplain ecosystem. And so, multidisciplinary approach is important for solving water problems.
Yeah, thank you. It also feels like, a lot of our open and collaborative research is also dependent on open access libraries and software. And there's a lot of questions, regarding the sustainability of the software, but our computational infrastructure are really dependent on these softwares and tools. So I'm just curious if, Quasi is also working towards sustainability of some of the libraries and software, or if you have any thoughts about it.
Well, yeah, I mean, that's part of our mission here is, and as I said, in some cases, fair data and modeling, it's as much a socialization activity as it is a technical activity, right? So, I mean, there are lots of metadata standards and people are starting to think about modeling standards. And so there's a real need, I think, to socialize this idea and to, you know, encourage the community, show examples of how it's valuable to share data and make data and code fair. So I think, you know, you kind of have to work along two fronts. One is improving the technical aspects of fair data modeling, but also socializing the idea, training people and making tools that people can use easily, so it's not a big bar to overcome.
So we have a next question from Martin. So he says, hi Gerard, thanks for the excellent presentation. Some of the computational science solutions, web services, etc., are sometimes too clever by half and do not necessarily match the way that hydrologists do their work. How do you think we can better bridge the gap between the hydrologist and computational science?
Yeah, I mean that's really kind of at the core of this thing, I think. And to me, you know, using Binder and Jupyter notebooks has really allowed us so again, like the case of Martin's class, students didn't have to upload and, you know, build their model. They could just run the model and, you know, pay attention to the analysis and pay attention to the data and not the challenges of compiling and bringing in all the libraries and so on. And so I think some of these tools that are kind of coming into broader use, Binder and Jupyter notebooks, have really help people who, you know, they're just interested in the data and the results, and they're not interested in, you know, doing a bunch of, you know, Python coding or complex compilation. And the Summer Institute this year, which is normally is a residential program at the National Water Center in Tuscaloosa, Alabama, some of the students ran a complex model, Delft 3D, which is a coastal computational hydraulic model. But we were able to compile that and load it using Binder so that the students kind of hit the ground running using Delft 3D, and there was not a kind of a major you know, bar to get over.
Thanks. Next question is from Wouter. He says, hi Gerard, any thoughts on the balance between the storing, sharing all data and sheer amount of data needed for large domain modeling studies? Our approach is to spend considerable effort on documenting the workflow that generated the data and sharing that instead.
Yeah, I mean, that's a problem that you know, HydroShare and Kawazi has had to face, because when people do these large scale, long-term computational models and they want to store all the results, then that gets to be expensive. And of course, people don't want to pay to share terabytes of data, but they want data available. And so, you know, it makes a lot of sense to actually share the computational workflows so that the results are repeatable. You know, I don't know about, for example, publication of journals. Probably the reviewers and the journals may want to see the data, and they may want to see more than the workflows. I'm not sure, but again, I think there's a socialization issue here of, you know, if we can repeat the results using, as Wouter said, storing the workflows as opposed to just storing the data, then that may be a more easier way to go, as long as the computational demands aren't particularly, too hard.
Yeah, thanks. Next question is from Al. Al, would you like to ask in verbally or?
Yeah, I just wanted to send it to everybody so they could see it too. But yeah, so from a practical perspective, Jared, and you've got a lot of history working on the practical side of things too, right? Because of your past work. Like most of this is voluntary, people contributing to the system or whatever, right? So I presume the heavy lifting is actually on the investigator to put it in. It's a kind of a three-part question. So that's number one. Given that I think the investigators mostly doing the heavy lifting to get it into the system, do you have staff in the background to kind of vet these things and look at them, make sure they're meeting standards and sort of appropriate? And then the third part of the question is basically, how many staff were required to kind of keep it all going? And then the last part of the question is, can you keep up? Like, is demand just going up and you guys are just trying your hardest to keep up? So it's a bit of a loaded question.
Yeah, so in HydroShare, it's not used very much, but there's a capability to rate data sets. So a user can, make a comment on a data set. And I mean, this is just users, it's not the owner. Users can make a comment. They can send an email to the person who owns the data to ask questions about the data and so on. Now, in terms of vetting the data themselves, we don't curate the data. I mean, you can upload kind of whatever you want, but if you get to the point where you want to publish the data with a DOI, then we do curate that to make sure that the data and the metadata are complete, and that the resource itself is appropriate for publication in HydroShare. In the past, we've had people load airline flight schedules into HydroShare, and we don't really need that. We curate it at the point at which a user wants to publish with a DOI. That, I think that's kind of how we do it and how we kind of try to manage it. There are other repositories. I think like Bicodemo that I mentioned, they curate all of their data. They look at all of the data. We have a different model.
Great, thanks.
We have another question from Martin. Martin, would you like to ask it?
Oh, sure. Yeah. Hi, Jared. It's nice to see you. Thanks for doing this.
Yep.
A question has to do with the transition to open science. So in the past few years, we've definitely seen a paradigm shift towards open science, and it's certainly increased the need and relevance for systems such as HydroShare, and it's been disruptive in some sectors of the community. So I was wondering if you can share some behind the scenes war stories associated with the transition to open science, or share what you see as the major challenges as we complete the transition to open science.
Well, I mean, the second one is easier to answer. I had to think about war stories. But the challenge is that I think a lot of users don't see the benefit of making their science open, or there's this kind of philosophy that I don't really want to share anything because I own it and I don't want you to take advantage of my work and so on. So I think it's the socialization issue. The other challenge is the one that Wouter, I think, mentioned, the challenge of these massive data sets and how to manipulate them, how to access them, download them if need be, or upload them, or do computations with these massive, annoyingly massive data sets, as somebody has called them. I think the stories that I can relate to are the ones that I used at the beginning, the examples. I guess another example might be, when people use HydroShare to store airline flight schedules and so on, they have used the resource for different kinds of things that aren't particularly appropriate. But the main thing is just, I think, encouraging people to use the tools. And everybody has their favorite tools, and no repository is one size fits all. Quasi is working now with EarthCam and Open Topography, two different repositories, to build a portal for the critical zone thematic clusters that will help guide the investigators to point them to the right portal in which to share their data. So I think that's a really, instead of building another repository for this or that or the other, let's use what we've got and make it easier for people to access those repositories.
Yep, no, that's perfect. I guess another way of asking this question, I'll provide my perspective, is that if we overlay open science with the FAIR principles, then what we've done is that we've done a really good job about making data and models accessible, and we haven't done so well at making them findable, interoperable, and reproducible.
Yeah,
And I think it's the other elements of FAIR that need a lot of attention over the next few years.
yeah.
Thanks, Jared.
You're welcome. Thank you.
Thanks, Marty. I don't see any more questions. So I'll just give a few seconds if anybody has any last question. If not, we'll be formally moving towards the conclusion of the webinar today. All right. Thank you again, Gerard. I also want to thank everyone that attended this webinar. The video recording will be available later today in Core Modeling website. Just a note that next week we'll be having Dr. Simon Papalexiu from the University of Saskatchewan, who will be providing a webinar on advances in stochastic methods in hydrometeorology. So please stay tuned. That will be all for today. Thank you again. Please stay safe. Gerard, do you have any last comment?
No, it looks like there's another question here.
Oh, okay. Oh, yeah. So there's a question from anonymous attendee. You mentioned that individual watershed research is not very transferable. How can that be changed to make it more collaborative and to contribute to a great whole?
Yeah, I mean, I think it's some ways it's a cultural change, right? Instead of me working in a watershed for 30 or 40 years and collecting data, but building these models that kind of take into account physical processes that operate on larger scales. I think there's a trade-off between understanding processes completely and building tools that allow water managers to make the decisions that they need to make in pretty short order.
Al, do you want to say anything?
No, I just wanted to say a special thanks to Jared for joining us, and this gives us a lot of food for thought for GWF. You've done a great job with Quasi, and yeah, it's pretty impressive to see, right? So there's lots more to come, is my guess, with Quasi and HydroShare, and we're hoping that GWF can contribute in a real way to that too, right? So stay tuned. Thanks.
Yeah, absolutely an important partner. Yeah.
Thanks, everyone. Have a good day. Bye.